Hello and welcome to the channel. In another YouTube channel I've seen the following problem. Given that x plus 1 over x equals square root of 3, find the value of x to the power of 100 plus 1 over x to the power of 100. It looked like the author of the video desperately tried to avoid finding the value of x. Instead of that, he found the sum of squares, then the sum of powers of 6, until eventually he got to the power of 100. I don't know how he managed to do it, because even though I respect the channel very much, and some videos are really interesting there, this time I had a strong feeling that a straightforward way would bring the result much faster. So I just checked that the answer matches my own, and wrote a comment about a different way of solving the problem. Here I suggested to solve a more general problem, where instead of 100 you have 10 to the power of n, where n is a whole number greater or equal than 2. Just a reminder that a power tower is evaluated from top to bottom. In this case we first raise 10 to the power of n, and then raise x to the obtained power. Please pause the video and think about solving the problem. Someone probably noticed that the given equation is not as straightforward as it appears to be. To start with, x is of course non-zero. Moreover, for a negative x, the left-hand side of the given equation becomes negative and cannot be equal to square root of 3. Therefore, x must be positive, and so is 1 over x. In this case, we can apply the inequality of arithmetic and geometric means, according to which the sum of x and 1 over x is not less than twice the square root of the product, x times 1 over x. Since the product is obviously 1, we find that the left-hand side of the given equation is no less than 2, whereas the right-hand side of the equation, square root of 3, is obviously less than 2. So we conclude that the problem is inconsistent and finish the video. But now, as you can see, the video is far from the end. The reason for that is that the equation becomes consistent if we allow x to take imaginary value. So let's remove everything that could get us away from the right track and find the possible values of x. To do that, we multiply both parts of the equation by x, then subtract square root of 3 times x from both parts of the obtained equation. This gives a quadratic equation for x. The discriminant is negative, which is what we expected, so the roots of the equation are obtained according to the formula minus b plus minus I times square root of the absolute value of discriminant divided by 2a, where I is what is called imaginary unit and its square is assumed to be negative 1. b is the coefficient for x, in our case it is negative square root of 3, but minus b in the formula is just square root of 3. Letter a stands for the coefficient of x squared, which is 1. Also, the absolute value of the discriminant is 1. So the square root of it is of course also 1. Thus we get x equals square root of 3 plus minus I, all divided by 2, which can be rewritten as square root of 3 over 2 plus minus half of I. But square root of 3 over 2 is cosine of 30 degrees, or cosine of pi over 6. While a half is the sine of pi over 6. So we managed to express the value of x in so-called trigonometric form, which in general looks like r times cosine of phi plus I sine of phi, where r is the module of a number, in our case the module is 1, phi is the argument of a number. For the values of x, we can assume phi to be plus minus pi over 6. As an alternative, the values of x can be written using imaginary powers. e to the power of plus minus pi I over 6. However, such a notation is not going to be used in this video. There is a convenient de Moivre's formula for raising a complex number expressed in trigonometric form into a power. According to this formula, the module is raised into the corresponding power, while the argument is multiplied by the power. Given that the module is 1, we don't need to worry about the module, only multiply the argument plus minus pi over 6 by the power. Since letter n is already used for the power of 10, I am going to use letter k for the power of x. So x to the power of k equals cosine of pi k over 6 plus minus I sine of pi k over 6. Using de Moivre's formula, we can also write the expression for 1 over x to the power of k, which is x to the power of minus k. So we get minus for cosine and sine. But cosine is an even function, so the minus cosine can be dropped. While sine is an odd function, in which case we have to take minus out of sine, turning plus minus into minus plus. When we add up the expressions, their imaginary parts are cancelled out, while the real parts add up to 2 cosine of pk over 6. We see that the sum of x to the power of k and 1 over x to the power of k is always a real number, and it doesn't depend on which of two values of x is used for its evaluation. The obtained expression is quite concise, but inconvenient for big numbers of k we are going to deal with. So let's remove the stuff we no longer need and divide k by 12. 12 is in general a magic number, but for this problem it is really miraculous. So we write that k equals 12 times q plus r, where the quotient q is an integer. In this case it is even a positive integer. But we don't care much about that, as we are more interested in the remainder r, which is also an integer, while in addition r is non-negative and strictly less than 12. Let's substitute the expression for k into the right-hand side of the previously obtained equality. Now we can divide the fraction term by term and get 2 pi q plus pr over 6 under cosine. Since 2 pi as well as any multiple of 2 pi is a period of cosine, term 2 pi q can be dropped, and we are left with just 2 times cosine of pr over 6, where r is the remainder of dividing k by 12. Since there are only 12 possible values of the remainder, we can draw a table listing all values of x to the power of k plus 1 over x to the power of k, corresponding to each possible remainder. However, this table isn't really needed for solving the problem. Try to complete the solution on your own. So the only thing needed to complete the solution is finding the remainder of dividing 10 to the power of n by 12 for an integer n greater or equal than 2. Let's prove that for these values of n, number a equal to 10 to the power of n minus 4 is always divisible by 12. Since 12 is 3 times 4, where 3 and 4 are coprime numbers, a number is divisible by 12 if and only if it is divisible by both 3 and 4. At start, we express 10 to the power of n as 100 times 10 to the power of n minus 2. Since n is no less than 2, the power n minus 2 is non-negative. Therefore, 10 to the power of n minus 2 is an integer. This means that 10 to the power of n is divisible by 100, and therefore by 4. While after subtracting 4, we get the number which is still divisible by 4. This shows that a is divisible by 4. To prove divisibility by 3, we express a as 10 to the power of n minus 1, then minus 3. We know that the number 1 less than 10 to the power of n is written with n nines. Such a number is obviously divisible by 9 and therefore by 3. Or, in a different way, since u to the power of n minus v to the power of n is always divisible by u minus v, then in particular 10 to the power of n minus 1 is divisible by 10 minus 1, which is 9. In either way, we prove that the first term in the expression for a is divisible by 3, and after subtracting 3, we get a number which is still divisible by 3. Thus, it has been proven that a is divisible by both 3 and 4, therefore a must be divisible by 12. This means that 10 to the power of n, which is a plus 4, gives remainder 4 when divided by 12. Substituting 4 for r gives x to the power of 10 to the power of n plus 1 over x to the power of 10 to the power of n equals 2 cosines of 4 pi over 6, which is 2 cosines of 2 pi over 3, which in turn is 2 cosines of pi minus pi over 3, which, according to one of the reduction formulae for cosine, is equal to minus 2 cosines of pi over 3. But cosine of pi over 3, or cosine of 60 degrees, is a half. Therefore, the expression is related to negative 1. That's the answer obtained by the mentioned video. And now we know that it applies not only to n equals 2, but to all greater values of n. So we write the answer, and this is the end.